All right, welcome back. Today, Chapter 3, Section 6.1, Principal Ideal Domains. These are very special types of domains, but they come up often enough and are useful enough that they deserve their own little section. All right, here's the definition. A principal ideal domain, PID as everyone calls them, is an integral domain in which every ideal is principal. That is generated by a single element. We've seen a couple examples already, namely the integers and the polynomial ring over one variable with coefficients in a field. They're both PIDs. For a non-example, polynomials over, say, the reals with two variables is not a PID. For example, to see why this isn't true, look at the ideal generated by x and y. So these are all combinations of xy plus gy. Then this you can mess around with. It's easy to show it's not generated by a single element. Okay, let's go to our first lemma. Let's start with D, a PID, and a bunch of A sub i's, a finite list, that are not all zero. Okay, up to a unit, there's a unique D in D, so up to multiplication by a unit. There's a unique D in D so that the ideal generated by D is the set of all linear combinations of the AIs, where the linear combinations can be anything in D. Okay, that's part one. This D is the greatest common divisor of the A sub i's. So really I'm saying two things here. In PIDs, greatest common divisors always exist, and those greatest common divisors, since D is in here, it'll be a linear combination of the AIs, just as it was for the integers. So that will be number 3. Let's write that. So here we go. They're BIs, so that D is a linear combination of the AIs for some coefficients BI. Oops, that shouldn't be a Z. There, now it's a D. All right, let's prove this. This, as you can see, is not going to be hard. Okay, for the proof of 1, this set of all linear combinations of the AIs is trivially an ideal. It's the ideal generated by the AIs. And since it's an ideal, there's a unique D that generates it. It's unique up to multiplication by units. So here it's written out. Since we're in a PID, there's a D, a single element that generates the ideal. And always, ideal is generated by a single element. That generator, as we've seen before, is unique up to multiplication by a unit. All right, number 2. We want to show that D is the greatest common divisor. So that is actually two statements. One, it is a common divisor. Let's start there. So here that is. The AIs are obviously in there. Take BI to be 1 and all the other B's to be 0. And since that ideal is generated by D, that means AI has to be a multiple of D, which just means D divides AI. So the D is a common divisor. Next, we have to show that any other common divisor will divide D. In other words, D is the biggest of those, is the interpretation. Okay, here's that written out. We need to show that if C is any other common divisor, then C divides D. All right, well, if obviously D is an I, so D can be written as a linear combination of AI, BIs, and since C is a common divisor, it divides all the AIs, therefore it divides any linear combination of them, therefore it divides the D, and we're done. So no problem there. So D really is the greatest common divisor. And for 3, well, I guess we already did it. All right, so that's the end of the lemma. Now let's go on to the main theorem of the section. Here it is. The theorem is that if you're a PID, you're always a UFD. All right, let's go to the proof. All right, we have greatest common divisors, and if you remember back to that theorem, one of the conditions for checking a UFD was that it had greatest common divisors and that it satisfied the ACCP, the ascending chain condition on principal ideals. So let's start with a chain of principal ideals. All right, so here's the notation. Suppose the AIs are contained in the AI plus 1s for all big I's here, I from, say, 1 on. And we want to show that it stabilizes eventually, that eventually they're all the same. All right, the trick is simply to look at the union of all these nested ideals. Normally, when you union ideals, you don't even get a subring, let alone an ideal. But on your homework, you've shown that actually if you take the union of nested ideals, you get an ideal. And that's easy to show. I'm not going to go over it again since you've done it. Now, since it's an ideal, and we're in a PID, that means it's generated by a single element. Okay, there it is. Let's say it's generated by alpha. Now, since I is the union of all these ideals, and alpha's in there in particular, it's got to be in one of these A sub i's. All right, now you can see what's going to happen. I mean, once you get up to at least I naught, alpha's in there, and that generated everything. So you're already as big as you can be, and everyone's stabilized. So here it is written out. You have the ideal generated by A naught. It's contained in all the A, I naughts plus K's, so in any of the farther down the road ideals. And of course, all of those are contained in I, because I was the union. However, since alpha was in here and it generated everything, this thing is already all of I. And so that means that since, well, you've got I here, this thing here is actually inequality, so it's stabilized. So we've got a UFD. PIDs are UFDs. All right. This is a handy theorem. PID is stronger than UFD. So we ought to get something more from it. And so there's one more theorem that we're going to give. All right, here's the theorem. In a PID, all these different categories are the same. An element P is irreducible if and only if P is prime. We actually know this one works for UFDs, so that's less than what you need as a PID. And then an element P is prime if and only if the ideal generated by P is prime. That's actually the definition, so that one's always true. But here's the new one, that an ideal P generated by P is prime if and only if it's maximal. So the prime ideals actually jump all the way up to maximal. Now, if you recall, we already knew that maximal always gave prime, so really the only work we have to do is this direction. All right, let's go to the proof. Okay, as we just said in words, really the only part of this that remains to be proved is that prime ideals are maximal ideals in a PID. Okay, so we'll be doing an argument by contradiction. Start with a prime ideal generated by P, and suppose that it's not maximal. So that means it's contained in some other ideal that's bigger. But since we're a PID, every ideal is principal, so that ideal would have to be generated by some element that we're calling B. So containment of ideals, you get the reverse inclusion is what that really means. So B divides P, same thing as saying P is equal to B times A for some A in your domain. But that A can't be a unit, and that's because this was a strict containment. If it were a unit, they'd be the same ideal. All right, well, what do we get now? Since we haven't used the primeness of P yet. Since P is prime, and P is this product here, it either divides the B or it divides the A. Well, in the first case, if P divided B, that just means everything in B is the ideal generated by B is contained in the ideal generated by P, and of course, because of this up here, we would have that B is equal to P, and that would be the contradiction because we were assuming that there was a strict inequality. Okay, if P divides A, well then A is P times C for some C in the PID, and we're going to combine this statement with this one. So we get P is equal to B, and then the A part is the PC. But then we can cancel the P's. Remember, we're in a PID, which is a domain, and that says 1 is equal to BC, which says, at the very least, well, exactly, it says that these are both units. All right, so we get B is a unit. Let's scroll up a bit here. All right, well, in that case, that means way back up here, this ideal that was bigger than P, since B is a unit, this is the whole PID. And that means that, in fact, this guy really was a maximal ideal because there's nothing that you can fit above it except for the whole space. All right, so that's the end of the proof.